Hello, I'm Omnik. Today I will be solving third division Cadifarsis round, um, what we can get, and trying to explain what I'm doing. Yeah, the competition started like 4 minutes ago, something. So let's just go into it. Haven't done videos for a long time, so I'm kind of rusty, forgetting what I need to do. Problem A, blackboard game. Initially the integers from 0 to n-1 are written on blackboard. In one round, Alice chooses an integer a on the blackboard and then erases it. Then Bob chooses an integer b on the blackboard such that a plus b is equal to 3 modulo 4 and erases. Rounds take place in succession until a player is unable to make a move. The first player who's unable to make a move loses. Determine who wins with optimal play. Well, it feels like there is no strategy, there is just fixed number of moves you can do, because basically we have like 4 groups of numbers, modulo 4, and those groups are split into 2 pairs. So if Alice takes numbers that is 0 modulo 4, then Bob has to take numbers that is 3 modulo 4, and vice versa. And if Alice takes numbers that is 1 modulo 4, then Bob has to take 2 modulo 4, and vice versa. So we have like all the zeros, all threes, all ones, all twos. And like if Alice takes a number from one group in the pairs, and Bob takes number from the other group in the pair. So basically, for Alice to win, she needs to make one group in a pair empty, but the other group not empty. So like they alternate moves, but then one group is empty, but Alice can take number from the other group from that pair, and then Bob will not be able to make an answer. And it seems that like we fill the groups like 0, 1, 2, 3, 0, 1, 2, 3, and so on. And so Alice will win if there are more numbers in group with 0 than there are numbers in group 3, which happens if and only if n is not divisible by 4. So Bob wins if n is divisible by 4, otherwise Alice wins. And that fits the samples, so yeah, we just need to check if n is equal to 0 modulo 4. If it is divisible, then Bob wins, otherwise Alice wins. So if n is not 0, I will return true and then print Alice, otherwise I will print Bob. Alice Bob, Alice Bob. Problem B, tournament. You're given an array of integers a1 to an. A tournament is held with n players. Player I has strength ai. While more than k players remain, two remaining players are chosen at random. Then the chosen player with the lower strength is eliminated. If the chosen players have the same strength, one is eliminated at random. Given integers j and k, determine if there is any way for player j to be one of the last k remaining players. So the strongest player will always remain, but if k is not 1, then any other players can remain, right? Because like the strongest one can eliminate everyone else. So if k is not 1, then it's just yes. If k is 1, we need to check that the like player number j is, well, the strongest one, but if it is equal, then like we can choose who wins basically. I don't like when like they say at random, but then ask if is there any way. So it's not random. It actually like we choose what happens, because like they ask is there any way to do it. So it's not random. We are randomness. We are choosing what will happen. So I don't like when people say at random when there is no randomness actually, when we are the ones who are choosing what will happen. It's not strict. Don't do that in problem statements. But yeah, going back to the problem, if k is not 1, then the answer is just yes. If k is 1, we need to check that our number is one of the largest, so it is not smaller than everyone else. Unfortunately, like as regular viewers would know, I like it very much when I can solve the problem without storing the input. Unfortunately, that's not the case here because we are given j. If we were asked to solve it for the first player, then I don't have to store the array. But since it may happen that, oh, actually, yeah, I can. I can remember the j's element, and I also can calculate the maximum while just reading the array without storing it, and then I will compare the j's player strengths with the maximum strengths. Oh yeah, so I can. Nice. And I don't need to store more than constant number of variables. Always like that. We need like hours and maximum. Okay. Double checked the order in which it is given. Hour 0, max is also 0. the values, updating the maximum, and if I is p, so that's our number, then our is x. And then if k is greater than 1, then yes, but also if k is 1, then our should be equal to max. Problem C, prefix min and suffix max. You are given an array A of distinct integers. In one operation, you may either choose a non-empty prefix of A and replace it with its minimum value, or choose a non-empty suffix and replace with its maximum value. Note that you may choose the entire array A. For each element AI, determine if there exists some sequence of operations to transform A into just an array of single element AI. Output your answer as a binary string of length n, where the ith character is 1 if there exists a sequence to transform A into AI and 0 otherwise. Well, it seems that our number should be either a prefix minima or a suffix maximum, right? Because like I cannot remove my number because I want it to be the end result, and like all the numbers are distinct. But even if that wasn't the true, I could like first determine which actual elements I can keep, and then just like remember their values and set the answer to true if and only if I can keep that value. But since all the elements are distant, that is not needed. Like there is our element somewhere in the middle. So if I take a prefix that is like going over my element, so like I'm taking my element in the prefix, then it must be the minimum value, otherwise I will remove it right now in this operation. So like it must be a minimum on this whole prefix I'm taking, which certainly means that it was a minimum on the prefix like up to this element. And the same with the suffix. If none of that happens, like it's not the minimum on the prefix to itself, so like, there is some smaller element before and there is some larger element after, then we cannot change that. Like no operation would be able to change that. For example, if there is an element before us that is smaller, like we cannot take a prefix that will take our element because that would kill it. So we can only take smaller prefixes. But then like the element that is smaller will be still there. Like we will remove some elements but not the minimum one. So the minimum one to the left of us will stay there. And the same true is for the maximum on the right hand side. So they will always be there and we cannot do anything about it. But if like the opposite is true, so like for it is either the like prefix minimum or suffix maximum. If it is suffix maximum, for example, so it is larger than everything to the right, so we can take suffix like up to my element, it will remove everything on the right. Now we can take prefix like up to my element not inclusive. It will compress all the prefix into one number, and then I will have just two numbers. One of them is mine, and then I can take like either minimum or maximum depending on what I want. I want mine element to survive. It is either minimum or maximum of these two, so one of those options will be good. So yeah, just for every element I need to determine whether it is a prefix minimum, whether it is a suffix maximum, or none of that. If it's none of that, then the corresponding answer will be 0, not possible. But if it is one of those things, then the answer will be 1. Cool. Yeah, here I think I have to store something of linear size. So let's just store the array. Okay, so you need to go left to right, maintain the minimum, and if the new element is the minimum, then set the corresponding answer to 1, and then do the same, but from right to left and for maximum, not minimum. Problem D, binary string battle. Alice and Bob are given a binary string s of length n and an integer k. K is strictly smaller than n. Alice wins if she is able to transform all characters of s into zeros. If Alice is unable to win infinite number of moves, then Bob wins. Alice and Bob take turns, with Alice going first. On Alice's turn, she may choose any subsequence of length k in S, then set all characters in that subsequence to 0. On Bob's turn, he may choose any substring of length k in S, then set all characters in that substring to 1. Well, that seems stupid. Oh, actually, no. Okay. I wanted to say that if Bob can make at least one move, then Alice cannot win, but that's not true. Actually, I think I will need to draw something. Okay, so here is our string. So obviously, if Alice wins on the first move, we can check that clearly. like just calculates the number of ones. If it is not greater than k, then Alice can take all of them and turn to zeros and win immediately. Like that's not an interesting case. So suppose Bob can make at least one move. So on the Bob's move, he can take some substring of length k and turn everything to 1. But if everything outside was zeros, then Alice will win the next move, right? Like she can take all of those ones and make them zeros again. So, but why would Bob do that? Well, he might not have a choice, actually. Like, if so, like before the Bob's move, something happened. So we had some string, and it might happen that like all the ones in that string are somewhere in the middle. Like there are some ones, otherwise it's just one. But like the segment of ones is kind of small, and it's in the middle, such that for any substring of length k, those ones will be inside that substring. Like if k is pretty large, for example, like let's consider a case when k is n minus 1, then Alice can win the following way. Even if everything was ones in the beginning, Alice can make first and last position to be zeros, and then all the remaining ones will be like in this middle portion that lies in intersection of all the possible segments of length k. And so after Bob's move, like we know that first and last characters were zeros before, and he cannot make both of them to be ones because they're too far apart. So he will choose some segment of length n minus 1, but it will leave one of the like leftmost and rightmost elements alone, and they will remain zeros. And so, well, one of them will remain zero to be zero, and then Alice can like take all the ones that Bob just made and make them into zeros and win. So yeah, and that can happen not only if k is n minus 1, but for some smaller values of k too. So, well, in any case, I think we need like 2 times k to be strictly greater than n, so that there are elements that lie in every segment of length k. Otherwise, like there is leftmost k and rightmost k. If they do not intersect, then either Alice wins on the first move or she just doesn't win, because Bob can always take either the leftmost or rightmost and like choose it in the way that some of the remaining ones were outside of the chosen segment, so that the number of ones after his move will be strictly greater than k, and Alice cannot remove all of them. So obviously checking if Alice wins on the first move. Then if 2 times k is not greater than n, then Bob wins. But what if k is big enough? So there are some elements that lie in the intersection of everything. I'm kind of tempted to just states that Alice will always win, but that is probably not true. Oh. Let's see. So, have a string. We have this non-empty middle section that lies in every and in every segment of landscape. Then Alice's like what she wants to achieve is that after one of her moves, everything outside that segment are zeros. If that is true, then Bob will make some move, but that move will cover this segment. So it doesn't matter that there were some ones. Now all of this is ones, but everything outside is just zeros. So Alice can make all of those ones into zeros on the next move. So Alice kind of doesn't care about this segment. She wants to make everything else to be zeros. Well, yeah, it can happen that this segment is just very big and Alice can achieve it on her first move. We can also check that, but what if she cannot? Yeah, it feels like she still should be able to make it all into zeros, like slowly and methodically. Basically, Bob's moves are kind of weaker because they have to cover this segment, which is of non-zero length, and which doesn't matter to Alice. So, on every Bob move, he can only like he will turn less than k zeros into ones if we only consider the positions that are outside this middle segment. But Alice can still turn k ones into zeros. So after some like finite, at most n actually moves, Alice can make sure that everything outside this middle segment is zero, and thus she will win. So yeah, we need to check if Alice can win on the first move. Otherwise, just check this condition. If this is true, then Alice wins. Otherwise, Bob wins. Okay, that's a nice problem, at least for like people like me who have this irresistible need to prove stuff instead of just like guessing, looking on samples. Is it the third problem out of first four where you basically print yes or no? So it's nk and string, right? If sum is at most k, then Alice wins, or if k is big enough, then also Alice wins. Otherwise, Bob will win. Problem E, max count. Defines the max minimum absolute value of an array to be the smallest non-negative integer not present in the array. You are given an array A of size n of non-negative integers for all k from 0 to n inclusive. Count the number of possible values of max after removing exactly k values from A. Interesting. So okay, so for a given k, there is some largest value we can get by just removing the largest. Oh, actually, never mind that. Like, the largest value we can get is just minimum of original max, because like it was the value that is not present. We can only decrease max by removing values. So it's minimum of original max and n minus k, because we cannot get max greater than the number of elements we have. After removing exactly k elements, we will have only n minus k left, and so max will not be greater than n minus k. Okay, so that is the largest possible max we can get, and look, we can actually get it just by keeping at least 1 0, at least 1 1, at least 1 2, and so on, until like we either reach n minus k or max of the initial array, which is like the smallest number that was not present, so we cannot go, like we cannot keep one occurrence because we hadn't have any occurrences. So that is the largest value we can get. And then for the, like, can we get some smaller value? Well, if we want our max to be equal to x, we just need to remove all occurrences of x and leave at least one occurrence of all smaller numbers. We know that we do have them, so the only thing we need to check is it true that we can remove all of the occurrences of x. So is it true that the number of occurrences was not greater than k? So it seems that for every value x from 0 to original max inclusive, we will have a range of values of k when this value is good, like achievable. Like the upper bound is n minus x, because if k is greater than n minus x, then we will have n minus k elements left, which is strictly smaller than x, so we cannot get our max to be equal to x. So the upper bound is n minus x. That's the largest value of k for which we can achieve it. The smallest value of k for which we can achieve it is the number of occurrences, because to be able to have this value as max, we need to remove all of the occurrences. So k must be at least this. So we have like k from frequency to n minus x. Like on this segment, it is possible to achieve x as max value. So to solve the problem, for every x from 0 to the max of original array inclusive, we need to like do +1 on this segment of k. Like for every k from the segment, we need to add 1 to answer. But since we do it offline, we can use like prefix sums, or difference array, whatever you call it, to like add 1 on segment offline. We don't need like fancy data structures, just prefix sums. In this problem, I don't need to remember the array itself, but I do need to calculate the frequencies. So I created an array for frequencies and an array for answer, in which I will fill it with zeros in the beginning, and then I will remember +1s and -1s that like define where I start adding 1 and then stop adding 1 in the answer, and then I will calculate prefix sums on it, and that will be the answer. So first we need to find the max of original array, and that we can do like with linear search. We start at 0 and like, do we have at least 1 0? If no, then that's the max. If yes, then like go to the next value and find the smallest value that does not appear. So while cnt of m is not 0, m plus plus. So now m is the max of the original array. And now for every x from 0 to m, say that the minimum value of k required is cnt, and the maximum is n minus x. So to be safe, you can like put if, like to check that the left border of the segment is actually smaller than the right one. That shouldn't happen. Like, shouldn't happen that left border is greater, because well, I know that for all the values smaller than m, cnt is at least 1. That's like how I define m. So this like none of those CNTs for x smaller than m can be greater than n minus m plus 1, because there are m values with CNT at least 1. I'm looking at one of them, so all other, like other m minus 1, they take at least 1 from total frequency, which is just n, the size of array. So the maximum value is n minus m minus 1. So, but like all the r's are at least z, and for x equal to m, this is just 0. So I can like assert that left border is smaller than right one, and then do my prefix sum magic. Alright, D was also accepted. 2 more problems to go. Problem F, minimize fixed points. Call a permutation P of length n good if GCD of Pi and I is greater than 1 for all I that are not 1. So for I equal to 1, this is clearly 1. So basically for all positions except the first one, the value on that position must not be coprime with the positional. Find a good permutation with the minimum number of fixed points. So yeah, obviously we can just put value I there to achieve that, but that's like not interesting, so we want to minimize the number of such positions where we just put the number. Well, for prime numbers that are greater than n over 2, we cannot do anything else, because like for a prime position, all the numbers that are not coprime must be divisible by that prime, but that is like, since all of our numbers should be smaller than n, it's not possible if the prime number was greater than n over 2. And it seems that like for all other positions it should be possible to yeah, and for position 1 we also we must put 1 there, because if we put 1 on some other position, then that position will not be satisfied, because GCD of 1 and something else is 1 also. So the first position should be 1, and all primes that are greater than n over 2 should also be fixed points. All others, like, it should be possible to satisfy them like without putting the same number. And yeah, it's not obvious clearly. And I need to actually print the permutation, so just saying that it's always possible without constructing a way is not helpful. Well, it seems that I can just like uh, split all the numbers into groups by their largest prime divisor. Then groups corresponding to like having no prime divisors, like as number one. This will be of size 1, and the groups corresponding to the prime numbers that are greater than n over 2, they will also be of size 1, just that prime number. But all other groups should be of size at least 2, right? Like for like big primes, but not big enough to be um, like basically between square root of n and n over 2 for those primes. Like it is at least 2, because if number is divisible by primes, then it is the largest one. We cannot have two prime divisors that are greater than square root of n. So since like there are at least two numbers divisible, then the size of that group will be at least 2. And for small prime numbers, there is at least like p and p squared, right? Like for at least for those two numbers, p is their largest prime divisor. So yeah, like I have those groups, and apart from the numbers that I cannot satisfy, inside like for every group I can just like shuffle the numbers inside that group. They are all not k-prime, pairwise not k-prime, because they have the same prime divisor, the same largest prime divisor. They might have like more common prime divisors, like GCD is not doesn't have to be equal to that prime, but it is at least that prime that the group corresponds to. So for every group it will be satisfied if like in my shuffle there are no fixed points, but that's easy to achieve. Just like make a like cyclic shift by 1, then there are no fixed points. Okay, so for every number I need to remember its largest prime number, which is like unusual. Usually you want smallest prime number, but like the way to calculate it is still just do the Ratosfen sieve. So I'm basically just doing the sieve, but instead of just saying that the number is not prime, it is divisible by something, I will just remember the prime that like cut it out, but like not the first one, but the last one. So I'm always rewriting it. So like if number x is prime, so it wasn't divisible by anything smaller, then for all the numbers that are divisible by x, it is divisible by x. And like currently it is the largest prime that divides that number. Maybe I will rewrite it later if it wasn't actually the largest, if there are some bigger primes that also divide that number. So now for every number I know its largest prime divisor. So now I will group the numbers by their largest primed user. So for every number from 1 to n, I'm saying that like in the group that corresponds to p of x, which is the largest primed user, just put that number. Now I will go through all the groups. If the group is not empty, just taking size, and then I will like take a cyclic shift by 1 and fill the answer like in the permutation. So on position bij, I'm putting the number bij plus 1 not k. If the group was of size 1, then it won't do like anything. I will still put the same number, but that only happens for the positions that are either 1 or the prime number that is greater than n over 2. So those positions like I cannot fix, so for them just put the same number. But for all other positions it will put something there, but something that is not k-prime. The last problem G. It's called modular sorting. 5 seconds time limit. Interesting. You're given an integer m up to 500,000 and an array a consisting of non-negative integers smaller than m. Answer queries of the following form. So assign the point, and then some number k. In one operation, you may choose an element ai and assign, so add k modulo m. Determine if there exists some sequence of possibly 0 operations to make a non-decreasing. Note that instances of query 2 are independent, that is, no actual operations are taking place. Okay, so we have an array, we have some assignments in point queries, and queries with number k. It is we can do plus k modulo m, and need to check if it is possible to make a non-decreasing. Well, that seems kind of dumb. Like, we can do a lot of operations like this. Basically, for every number, like, we can do plus k plus k plus k as much as we want. So basically, for every number, like, we can transform it to some other numbers. How to understand to which numbers we can transform? Well, it turns out that basically we need to look at GCD of k and m, because, like, suppose, okay, let's look at it. So we had some starting value, and then we add k several times. Let's say d times mod m. So initial value is not important. Like it's important how much we add. So basically, we can assume that this is zero, and we want to look like from zero what can we get, and then from any other number it will be like the same but shifted. Right. So what values can we get as like k times d mod m? Well, it turns out that if we look at GCD of k and m, then all of those values are divisible by GCD. Because, well, basically, k times d mod m is like k times d minus m times l, where l is like k times d divided by m rounded down. So basically we're interested in like what numbers we can write like in this form that are also like between 0 inclusive and m non-inclusive. That is like well-known thing. What what's it called? Can't remember. Some like Bizu identity or something like that. The the numbers that can be written in this form, or rather, like it will be a plus, but d and l can be negative, or positive, or zero, whatever. So numbers of this form are exactly multiplies of GCD, because well, in one direction is that like all of those numbers are divisible by GCD clearly, because like k is divisible by GCD and m is divisible by GCD, so the sum is divisible by GCD. But then like we can show that we can achieve GCD, and then like by multiplying d and l by whatever, like we can get whatever multiples of GCD. And to show that it is possible, like basically like we can construct an algorithm that provides those d and l, and that algorithm is called extended Euclidean algorithm. So yeah, so the numbers that can be k times d modulo m are just multiples of GCD of k and m. Now, if we have like initial value, then whatever we add are like any multiple of GCD. So basically, what we can get are like this number, like what we can make it into. Like the property is that AI and BI are equal modulo GCD of k and m. So basically, now if we have an array, we are given number k, we want to transform it to some other array like with this property for every index, such that it is non-decreasing. How do we do that? Well, it's actually pretty simple. We can do it greedily. Like, let's make a1 to be the smallest number with like correct residue modulo G. Then b2, we can again like make a2 like to be the smallest, but if it is smaller than b1, then like add G until we make it like not smaller, and so on. So what if we look at those values just like modular g? So let's say that ci is ai mod g. Then like if we plot those ci, we will see something like this. So we start at some value, then they like increase, maybe like stay at the same level, but then there will be like a drop. Then they increase again, then a drop. There can actually like be like several drops in a row, but we can split the array like in between those drops and see that like in every such part between two consecutive drops we will add the same number of g's. So like here we are not adding anything. Then after the first drop we need to add g here, but then we will add g here and here and here. But then after the second drop, like adding g is not enough anymore, so we're adding 2 g's and so on. So here we're adding 0, then we're adding g, then 2g, then 3g, and so on. How many g's can we add? Well, it is like m divided by g minus 1 at the most, because like all our numbers should be smaller than m. So if we add m divided by g times, we will add m, and that is bad. But if we add like strictly smaller than that, it's good. So to answer one query in the original problem, we would need to look at this array C, look at like how many drops there are, and compare it to this number, where G is the GCD of K and M. But like, we cannot just do it for every query. That will be too slow, right? So the kicker here is that we don't really care about the value of K. We only need the value of GCD to do that. Like, if different values of K have the same GCD with M, they are the same for all intents and purposes. In this problem, I mean. So we actually care only about different values of G, and G are divisors of M by definition. Like it is greatest divisor of K and M. M is fixed, so G's are just divisors of M, and all possible G's are divisors of M. And there are not that much of them. Like the number of different divisors is well, there is like this heuristic that it's cubic root of M. That's just bullshit, but it provides like reasonable estimation for the values that appear in competitive programming. So for so in this problem, M is up to 500,000. If I'm not mistaken, then for million, the maximum number of divisors is 128, I think. It's either for a million or like 100,000. But like in any case, it's somewhere between 100 and 200. So we will just so the idea of the solution will be to like for given m, just generate all possible values of g and then we will basically solve the problem independently for every value of g. And like you can imagine that we can either just do it in parallel, solve for every g, or we can like read all the queries, generate all the values of g, and then just like go through all the queries for g equal to 1, then for g equal to 2, then for g equal to like next divisor of m, and so on. For all divisors of m, we just go through all the queries, apply all the operations, and we will maintain like the values that are needed. We will maintain that array C, and we will maintain the number of drops we had in that array. And then like to actually answer the query, we need to compare the number of drops with this value. So yeah, you can either just do it in parallel. That will take like n times number of divisors memory, like that number of integers. I mean, we don't actually need to store those integers. Those integers are just AI modular divisors. So for every divisor, we can just store the answer, like the number of drops, but don't store the array. Yeah, then like the memory is just linear. Yeah, that's one way. The other way would be like to just go through queries every time for every divisor, and like, in any case, like either we are doing it in parallel, and then for every query we're going through every divisor and updating the values, or we just like for every divisor we go through all the queries every time. In any case, like the total number of operations will be proportional to number of queries multiplied by the number of divisors. We need to be a bit careful that like it is guaranteed that sum of n and sum of q do not exceed 10 to the fifth, but sum of m can be big. So we cannot do anything linear of m, including like clearing anything. But we can do square root of m, right? Like 10,000 times square root is fine. If we couldn't, we could like pre-calculate all the divisors of all the numbers up to 500,000. But like it's fine to just factorize every time. Factorize m for every test. That's all right. Okay, let's do it. Yeah, f is okay. Okay. Okay, so first I need to find all the divisors of m, which will be my potential values of GCD. So now I have like those k divisors. For every divisor, I need to maintain the number of drops if we consider array modulo that divisor. So let's calculate the initial values. Okay, now I'm reading the queries. For the query of the first type, I need to read the position and the new value. And I need to update all of those numbers of drops when I replace like value on position P with the new one. I can change like the drop before this and after. So I guess I should like write a function. Here I can just write ans I plus equal drop j divs I, and here I will iterate over all the divisors, subtract the calls to drop before the change, because I did the like ifs on border conditions inside the function. I don't need to care here, like if P is the first element or the last element. I could just call the function, and if it's on the border, then it will just say, oh no, there is no drop there. It's fine. Then I change the value and then add the drops back, but like not back, but the new drops. So now I need to calculate GCD and then find it in the array of divisors and then like compare, well, basically print the answer for that GCD. I could just call a function GCD and then find it in the arrays, which is like the normal thing to do, but the thing that I want to do is just run through that array and find the largest value there that divides x, because like this is the list of all divisors of m, so to find the greatest common divisor with m of given value, I can just like try all the divisors I have here and find the largest one that divides x. It is kind of stupid, but like that's the kind of things I notice. Like it's kind of like simpler. It doesn't make the complexity worse, because I mean I could use binary search to find like where the position here, but I wouldn't if I just called GCD function and then I need to find the position in this array, I would just make linear search anyway. And like what's more important is that the other type of query already takes like linear of k time. So if I take linear of k time for this type of query, it doesn't matter. So I don't know. It's just like it seems fun to like not overkill or kind of in a way like I'm abusing the like what the problem asks me to do instead of like doing it in the most like straightforward way. I'm doing it in the simplest way under the limitations of what I already do for to solve this problem anyways. So like I will do linear search anyways, so let's just use linear search to find GCD. It's fun. So I need to find the last position such that x mod divs of I is 0. And now just is it just yes no? So now if check yes, otherwise no. So the answer will be yes if the number of drops is strictly smaller than m divided by this. So you can remember that like when I read the statement, I was like, well, this is stupid. And well, then I described a lot of stuff. But for me, like it's a trivial problem, right? Like I understand that this is like just about comparing with GCD of KM, and the number of possible GCDs is small. So, and then like I just solve it in a stupid way for every possible value of GCD, and like it's it's a lot to explain. It's like some code. I wouldn't say like a lot of code to write, but like some code to write. Probably much more in than all the other problems in this contest. But like uh, in the solving department, there wasn't anything, and like I think D is a more interesting problem than G. Uh, Probably even like E and F is more interesting problem than G. Yeah, I like D. Everything else is, and G is really not an interesting problem. Um, and why is the time limit is 5 seconds? Unclear. Alright, that's it for this third division contest. Well, at least I can solve third division contests in like hour and a half with commentary, but yeah. I think for the last couple of second divisions slash educationals, I did not solve everything in time. But yeah, here I can still solve something. Thanks for watching. Goodbye.